Krishna, turn on your mic.
Yes, sir.
Start. Okay, we can start.
Hearts. With warm greetings, I extend my warmest welcome to one and all invited here. This is Sai Krishnan pursuing my engineering degree in the Department of Electronics and Communication at Chennai Institute of Technology. We are analog beings living in a digital world facing a quantum future. Chennai Institute of Technology, the college has not left any stones unturned in making its students worthy citizens. The time as a caterpillar has expired and the wings are ready. Yes, it is about transforming lives. It's been just 10 years since CIT has stepped in, but the victories are huge under the successful guidance of our honorable chairman, first generation entrepreneur, Sri P. Sriram. It is indeed a privilege for all of us to get the opportunity of attending these webinars. To be short and crisp, yes, it is all about Knowledge 4.0. Today, we have our expert Dr. Rajbabu Velmurugan from IIT Bombay and our organizing secretary Mr. Eric Clapton. I feel much pleasure in welcoming you all. Now, I request our organizing secretary Mr. Eric Clapton to give a brief introduction about the session. Please, sir.
Good morning to all present here. I'm very happy to welcome all of you to the one-day seminar on research challenges in sustainable IoT, the reliance of 5G wireless networks and image co-segmentation under Knowledge 4.0 webinar series. This is one of the trend-setting and innovative initiative of Chennai Institute of Technology (CIT) established in the year 2010. Within the short span of time, we achieved top 10 position among 522 engineering colleges affiliated to Anna University Chennai. Knowledge 4.0 webinar series going in a very successful manner under the guidance of our Honorable Chairman Sri P. Sriram, the first generation entrepreneur, a well-known intellectualist and managing director of MK Group of Companies. We have been conducting various webinars under this webinar series such as technical webinar, research webinar series, innovation webinar series, and career guidance webinar series. In addition to this webinar series, we have also been conducting FDPs, workshops, conferences, and seminars. Now I heartily welcome our today's expert, Dr. Rajbabu Velmurugan, IIT Bombay, on behalf of Chennai Institute of Technology. He will deliver lecture on research scope on image co-segmentation. I also welcome all the participants from all over India to the seminar and hope that you will have a great time ahead. It is going to be an interactive session. If you need to interact with the expert, there is an option in your screen, request to speak. Once enabled, you can ask your queries to the expert. Now I call upon Sai Krishna to introduce.
Your,
Yes, sir.
your audio is off. Like I couldn't hear the last 30 seconds. Hello, can you hear me?
Yes, sir, yes.
Yeah, your voice got cut off. But anyway, that's not important.
Sai Krishna, you
Yes,
can
sir. Yes, sir.
introduce the expert.
Speaking about our guest profile, Rajbabu Velmurugan has done his Bachelor of Engineering degree at Government College of Technology, Coimbatore in the year 1995. He did his MS at Clarkson University, Potsdam in 1998 and his PhD at Georgia Institute of Technology, Atlanta in 2007. He has enormous interest in statistical and digital signal processing, audio and speech processing, and also in image processing and computer vision. He is currently working as Associate Professor at IIT Bombay. Now, without any further ado, I request you to take over the session, sir. Please, sir.
Yeah, so thank you for the kind introduction and for having invited me to give this seminar. So the talk which I'm going to give today is mainly on image co-segmentation, which is a very specific kind of segmentation. Just to, I mean, I'm not sure whether how this fits into the whole context, but I think it's still, we are talking about IoT and other things. The way this fits in is you could consider this as an application which may run on an edge device, trying to segment a common object from two different images. Okay, so that's kind of how it might fit. And then after that, what I'm going to talk today mainly is on just the techniques for this co-segmentation. So now let me get started with this presentation or the talk which I wanted to talk about today. Okay. Is the slide visible?
No, sir.
Is it visible now?
No, no, sir. So third icon. In the top, third icon, sir.
It's still not visible, or?
No, no, sir. Not it.
Okay, just 1 minute.
Sir, in the top, third icon, you can click that.
Yeah, that I can do.
Share that, sir. After clicking the share that.
It's still not visible.
No, not it, sir.
So just 1 minute, maybe I have to reopen the application. Let me. Is it now visible?
No, sir.
Okay. Just 1 minute. Yeah, I think. I mean, if you want, just. I think others are also listening, so maybe.
Excuse me, sir.
Yes.
Yeah, yeah. You are you pressed to turn screen share on, sir?
Sorry.
In top, we have third icon, sir.
Yeah. So I did that. I think what happened is.
If you did that, now the one more window will open. In that share entire screen will come, sir.
Yeah. So.
You just click that entire screen. You select that window. Morning we did no, sir.
Yeah. So just let me.
Okay, sir. Otherwise, we'll go for one more after,
But
sir.
give me a minute. I think I should be okay now.
Yes.
So I'm just re-entering in another window. Can you please enable me in that?
Yeah, sir. So, dear participants, kindly wait for 2 minutes. Sir will join again.
Yeah, I am.
Yes, sir. Turn on your video, please. Yeah,
So
fine. Yeah, fine, sir. Minimize this.
now you can see my screen.
Yes, sir. Fine, sir. You can start now.
Yeah. Okay. Yes. Sorry for that minor glitch and starting problem. Anyway, so let's come back. So as I mentioned, today I'm going to give you a brief overview of this work, which we refer as image co-segmentation. Let's get started and see what this problem is. So essentially, this will be the outline. So I'll introduce you to some methods, which we start with some unsupervised or so-called traditional approaches, and then more recent work which we have done using machine learning or deep learning, which is very popular nowadays in image processing, computer vision, and many such fields. So what is this problem of image co-segmentation? So here, just give an illustration of the problem. You have many images. These images might have been taken from the internet, and our objective may be to extract a common object across all these images. So many times we may say what this object is, but at times we may not want to say what the object is, but just say, okay, find everything common across these images. So of course, as humans, this is very easy for us to do. But if we are looking at it as a machine or a computer algorithm which is trying to do this, there are going to be several challenges. So for example, you can just take all these images shown on the screen. You have about 6 images where 5 of them do have a tiger, one of them has a bear, and even in one among the 5, the tiger is kind of hidden in water, and so you can see how difficult it could be for any standard algorithm. So this is our objective in this problem, that is, given all these images, segment out the tigers here. Of course, we could have segmented the bear also, but here we detect or say that this bear is an outlier, that is an object which we are not interested in. Okay. So this is kind of what the problem is which we are going to discuss. So of course, if you just look at segmentation, what segmentation does is it takes one of the images and segments out or extracts out one dominant object from a given image. So this is what we are going to look at. How we do it is what we will see as we go forward. A slightly different set of images to show kind of the problem a little more closer. So here there are 2 input pairs. The first input pair is a pair of tigers where we want to extract tigers. So that seems like kind of easy for a human eye, and I think the image algorithm also can do reasonably well. Whereas if you look at the second pair where you have 2 aeroplanes, so one aeroplane is front looking and the other aeroplane is a side looking aeroplane. So of course we could say, if I'm just looking and interested in extracting aeroplanes, if that is my statement, then I can extract these segments as the aeroplanes and say, here I have extracted the common object. But if we don't say such thing, that there is an aeroplane and we don't give any label to the object we are interested in, but we still want, let's say, this algorithm to extract this common object, that's very challenging, right? Unless there is some commonality across these objects, that is these aeroplanes in these 2 right side images, the algorithm is going to find difficult. So what we will see is how, if we don't give any information, these algorithms perform on this kind of different inputs, right? Of course, for simplicity, I've just given a pair of images. In a real world application, it may not be a pair, we may have many such images, and we may want to extract this common object, right? So where are these things applicable? One possible application is, this is more useful for machine learning algorithms. So many times machine learning algorithms need ground truth, which means they need to know what is there in an image, what kind of object. So, but then there may not be labels already existing, but we may have labels for few images, and the remaining few may not have this label. So what we could do is we could co-segment all these images, and as long as the segments match, then we can use the same label across all the images. So we have kind of quickly obtained labeled images which can be used for training a machine learning algorithm. Another slightly kind of difficult or maybe more challenging problem is if you have, let's say, videos instead of images, and these videos, let's say these are from movies or some serials kind of thing, but we want to identify and extract out common segments, a certain set of sequence of actions from any of these videos. So then you can think of this image co-segmentation being extended to a video co-segmentation, and we are co-segmenting many such videos. So that's kind of the applications of image co-segmentation, where one could benefit from image co-segmentation. Of course, there has been work in this area, though not as wide as in segmentation itself, but somewhat restricted kind of area. They started off with traditional segmentation like approaches, where it's essentially doing 2 multiple single image segmentation and then trying to find how these segments match. And if the segments match, then that is co-segment. If they don't match, then they are different images. Moving on, there were some supervised approaches, or what I would say semi-supervised approaches, where a human is involved in it. So they take multiple such images where there is a common object, and they just do a scribble on these images. So anywhere the images is scribbled, that means this is common across these images, and an algorithm, kind of a traditional algorithm, goes over these images and extracts the scribbled region as segments. The third, again, like a popular approach is to use saliency. Saliency essentially says that some object is kind of salient in a given image. Salient means dominant. So if you take many such images, you look at each of this image and try to find the dominant object image on that image, and you segment out that dominant object. So this is also will lead to again common objects, and which you could extend to extract out these common segments across the images. So our approaches to this, the first approach we start with is what we call as a subgraph matching kind of approach. We will soon see why we call this as a subgraph matching. Essentially because we start the problem by using a graph representation for an image. And once we represent these as graphs, then we have to identify common parts of the graphs across the two different images. So we kind of extended it to not just segment pair of images, but even multiple images, so that our algorithms are not restricted. So for example, in this case, there are 5 images, and there are 4 images which have a kite, and the 5th image doesn't have a kite, it has a panda bear. So we would, given all these 5 images, we would extract only the kite regions and not the panda bear. So we had a modification of our original algorithm which helped us do this or address this multi-image problem as well. The third and more recent approaches which we have done uses supervised approaches, which means we have a image data set where we say, here are all these images with some co-segmentable object. We train a network so that it learns how to co-segment given a pair of image. And once it knows how to co-segment a given pair of image, you give any test image, it will co-segment those test images as well. The last one is still a supervised, but it's semi-supervised in the sense, typically to do this co-segmentation problem, we need a very large data set. So what do we do if we don't have a very large data set? If we have only few images and we can't train a model, how do we achieve this similar performance? For that, we look at what is called as few-shot learning. So let's see how we go about doing this. And before doing that, here is a way, if I'm using one of the existing approaches, here what is shown is there is an input pair at the left side. So we apply an algorithm which finds saliency in each of the image. So once you do saliency, you can see that the cows are kind of highlighted or extracted out. And if we now do a co-segmentation, you can see if we do some comparison of this cow image or segmented cow image, they will be very close and we could co-segment. So this seems to indicate that saliency is a good way to do co-segmentation. But just as a counter example, here you see again an input image pair. One on the left pair, one has a rose and the other has a bird flying. Of course, it's not a very realistic example, but still, let's say you apply saliency to these images and try to co-segment, you may end up saying that this bird and this rose are common or similar object, right? But that's not what we want, and hence we have this kind of algorithm which is we are going to see more in detail. So the starting point for our method, as I mentioned, is going to be a graph representation. Of course, many of you may not have done a lot of image processing, or maybe even if you have done image processing, you may not have done something more advanced. So since I don't really know the kind of exact background of all of you, I'm just giving some quick introduction so that you can still follow what I'm saying. So given this image, you could think of an image consisting of many pixels, that is each, let's say, dot in this image is a pixel. So you could think of taking all the dots and think of that dot as a node in the graph, right? If you do that, what you would see is there are many nodes in the graph which are connected. And for example, if you think of a node at this corner, that may not be connected to a node at the extreme corner, right? So that is how, if I think of just the pixels, if I try to form a graph, I will have a very huge graph, and doing anything useful with that will be very difficult. So what we do, instead of representing this image as a pixel, we represent it as using superpixels. What are superpixels? The superpixels are something you can think of, it's a large pixel. So the way superpixel is different from a pixel is, you can take this image. On the left corner, I have one large area like demarcated by this fluorescent edge, right? So all the pixels within this region are homogeneous. That is, they are similar in some form. In this case, just think, for example, like color, right? So they're all similar in color and few other aspects. Hence, that forms one superpixel. Similarly, what we do is we take the entire image and make many superpixels instead of having pixels. So now, instead of having, let's say, if this is like a 300 by 200 image, instead of that many number of pixels, we have about 50 superpixels. So this is first superpixel, second superpixel, and so on, right? So this superpixel representation essentially helps us represent this image in a very few kind of samples, or if I'm going to use it as a graph, then few nodes. So this is kind of a starting point for the unsupervised methods which we do in this work. And there are good algorithms which do this superpixel segmentation. Okay? Of course, as mentioned here, I told a very basic example of just looking at the color. So if you see color, I think you will see already that the superpixel itself will be very large. So instead, we look at something more specific, which is CIE lab color, which means it's going to use these RGB values and then slightly a transformed version of these RGB values, and only then they are similar that homogeneous regions is looked at. Similarly, we also look at slope or smoothness in the image, and these two features are used to compute the superpixel. So here, this image of this crane has been segmented into just give superpixel. So this is a good starting point for our next step. Once we have such an image and we have obtained, let's say, superpixels for that image, what we do is we take each of the superpixel and say that superpixel is a node in the graph. So if this is a node in the graph, so this corner superpixel is connected to the three adjacent superpixels, right? So then what, actually in this case only two, because this is not connected to this one. So it is connected to two superpixels. So what we do is we use this information to represent an undirected graph. We form an undirected graph using all these node superpixels, and two nodes will be connected if they are adjacent regions, and they will not be connected if they are not adjacent. So once we form such a graph representation as shown in the C here, we could visualize and say that a subset of this graph will form the object of interest for us, and that is shown in this D. This subset, if I put back the features here and go back to my image representation, I will get back my image, right? So this is essentially saying that you start with the image, obtain superpixel, represent it as a graph of the node or node of the graph. Then you form a graph which essentially is called as regions adjacency graph. For those who have done any computer science course might be familiar with. Essentially use nodes lying adjacent. And then in that, you extract out a subgraph of that RAG to get your object. And this object is what we are interested in. And we will see how now we move forward. So now the thing to keep in mind, each object will be represented by a subgraph, and each node in the subgraph is like a feature. Of course, it may be misleading to think that the way the graph laid out here is exactly how the image should be. But please remember that's not the case. When I'm just looking at it as a graph, I can just make this pull this nodes of the graph far away, and that doesn't mean any change in the actual object, because we have to map each of the node here back to the image. So that is what is important. The feature which this node represents is what is important, not necessarily this length here. These are all just for visual representation. Once we have such a representation for one object in one image, we can think of our co-segmentation problem. So we will have two images and correspondingly two graphs. So here represented using V and U as their nodes. And now we want to find what are the common set of nodes and the corresponding connections in these two graphs, right? So that's why we say that we are interested in extracting the common subgraph across these two images or two graphs, right? Of course, if you just see the structure of the graph, you would seem to think that, okay, this is exactly the same graph. Of course, there is slight variation. But what we want is we want to compare. If you form a graph using the one which is shown here, V1, V2, V8, V7, and this is the right side, U1, U2, A8, A9. These two, if you go back to the image plane, will look like or will correspond to a similar object. So this is what we want to find. And that we do instead of comparing the image features, we are using only certain graph nodes and then comparing the features in those graph nodes. So if when we do such a comparison, this is not one-to-one. That is, you can see that the two different images may have several regions which are similar in color. They may not be exactly same, but they may be similar, right? So that means an object in one image, or if you take one node in an object, it may correspond to many nodes in the other image. But what we want is we want only the nodes which are connected or which are similar in the way this image on the left side has. Okay, so we have to look at what this many-to-one matching is and pick a meaningful matching subgraph between those two objects. Because there are some algorithms from computer science which help you find this connected set of nodes and correspondingly the common object. I'm not going to the details of this, but if you do that, what you would end up is this is like just shown in images, and the input image pair is shown on the left. We do a superpixel segmentation. That's the one which is shown in the second column as superpixels. And in the third column, after running our algorithm on the superpixel, of course, I have now not showing the graph in between. There was a graph representation for both these images. We compared the graphs and extracted the common objects, and that's what is shown in this third column. That MCS is maximum common subgraph matching. So of course, now we have not yet covered or given the color from the original image, but we have just shown the spatial regions which are common across these two images. And if we map back to the original color from the original image, you get this partial object which is shown in the fourth column. So as you can see, though, we have extracted out most common regions across both these images, there are still some patches which are missing in both the images. Okay? So this is to say that this is the best our just graph matching helps. So beyond that, what we do something typically done in image processing, which is what is called as this region growing, but we do slightly different. We do region co-growing. That is, we fill in this patch based on something from the other image, not just this image, so that this is what we are interested in. The input image is what you are interested in. So we do this using some, again, similarity kind of measure. And once we complete that operation, what we have is the one which is shown on the rightmost column. Right? So if now we have this complete objects extracted, given the original pair of images. And so at this point, our algorithm stops saying that, okay, now we have extracted common objects across both the images. So this is one way, or this is the way our algorithm works. We had this published some time back. And here is again an illustration of this algorithm working on an image which has trains as its input. So you can see that there are kind of the background is quite different. One train is looking, the direction which the trains are moving or looking at is different. Despite that, you can see the last but one column, which is the result from our method, seem to have reasonably extracted the train images. So you can compare this proposed output to the ground truth output, where you see the trains alone shown as segmented regions. So we seem to have done reasonably well compared to other existing algorithms, which may not have done that well. So this is kind of one of the outputs of the algorithm. One thing which we would also want to do is, if the image size becomes very large, so then we can't, we will be able to do this algorithm, but the graph matching and others will take much more time. So instead we can do something more effective or maybe efficient. And here we do something which we typically do in signal processing. I'm sure most of you would have done DSP courses. So you do some kind of downsampling of the original image. Of course, when you do downsample, you have to be careful that it doesn't introduce aliasing and other aspects in signal. So similar thing has to be made sure here as well. But what we could do is, with a reasonable downsampling size, we can assure that the original image features would be captured in, say, a few set of superpixels. And once we do the matching in the superpixel graph based representation, we can map back and get the original image in its original resolution. So this kind of approach helps us in saving time and without losing much of the quality. So for example, as the image size increases in some order, let's say as it increases to a factor of 16 by 16, our proportionate increase in computing time is not that high compared to some other existing methods. This is much efficient in terms of computation. Of course, here it's just a simple signal processing trick which helps us achieve this kind of computation improvement. So I think at this point, this is kind of a natural transition to see how the algorithm works. And I would like to see if there are any questions at this point before just moving on. Okay. I believe.
Questions, Ishmael. You're waiting for
Yes.
questions,
Any
sir?
questions?
Right, sir. I will ask the participants. Dear participants, if you have any question, kindly give request to speak. Dr. S. Chandrakant, I have enabled you. Dr. S. Chandrakant, I enabled you. You can join with us now.
Yes, please. Any question? If not, I can continue.
Jayashree, sir, you complete, sir. At the end of the session, we'll take the question, sir.
And no question. So,
Yes, sir. End of the session, we'll take
okay. So
questions.
let's just
You
continue
can
then.
continue. Yeah.
Yeah. So we kind of extended this graph-based approach to do handle multiple images. Here again, this is you can think of as this common subgraph trying to be now done as a maximally occurring common subgraph. Again, this is something which we introduced. So the main idea here is that rather than just looking only at pairs of images, if you just do that pairs of image based common subgraph matching, and if you consider, let's say, for example, the last two pair, the polar bear and the kite, if I use this pair as my input to previous algorithm, I will not get anything common. So since I don't get anything common in this pair, the entire output of this co-segmentation algorithm may just, even if I do pairwise, will be empty. So instead, what we wanted to do was, we wanted to introduce an intermediate step where we build on from the previous pair, right? So that at the end, we will actually, even though there is one outlier, we can get all the objects which are common across other images. The approach for this is somewhat intuitive in some sense. What we do is we kind of do a similar course representation using Superpixel, form the graph. But then what we do kind of clustering of the nodes across all the images. So we have, let's say, 10 images here. We get nodes from all these images. We cluster that images into many clusters. So we decide the number of clusters, let's say 10 clusters or 5 clusters or 6 clusters. So here I'm showing you an output, if we, not output, a partial output of 4 clusters. So you can see in one cluster, that's the first row, there is nothing significant about the object itself. Whereas if you look at the third cluster, it seems that it has captured the bear in most of the images. So this is something what we call as kind of a dominant cluster, or a cluster which has a very compact kind of cluster. So this cluster will certainly be there in the co-segmented region. So what we want to do is we use this kind of as a starting point, and every image we grow to bigger and bigger regions, right? So that instead of just using a pairwise, we keep on growing across all the images and form something what we call as a latent space, which is much larger than all of the image clusters here, right? So once you have that partial object, we start growing in something similar to a region growing. So for example, we start with H1, which is from image 1, then we build to H2, we keep growing this graph, and when we keep growing this graph, at the end we will have a much larger graph, which will include all the regions which we have covered until now and something extra, right? So that's why that graph, which we call this latent graph HL, will have some more nodes, but we can't really map it back and say here is an object. So then what we do, we go back again and then say start using that latent graph and compare each of these images and fill in those images the segments which are missing. So if we do that, then we kind of get back the original object across all these images. So this representation of latent graph is something, by the latent means it's not something which we can see visually. And there is, if I map that graph to a physical object or the image, we may not get anything useful because this is some space which we don't really which can't be really visualized, right? But this makes sure that all the objects across these images are consistent. So here this is just showing it in a slightly different and precise way. You start with this H1 and H2, that these are the two graphs corresponding to image 1 and image 2. We obtain something common, and that something common is called as a latent space. Anyhow, here at this two images it says HL2. We keep growing this HL across all these images, and the end we have this HLM, right? This HLM is now compared with every other H1, H2, HM, so that they are also built upon. So I'm not going to go too much details into this, and here are kind of the results using this method, where we can see that even if there are multiple images and there are 8 common objects and 2 don't have a common object, which matches with the ground truth which is shown in the last row, right? So we can successfully co-segment all the common objects and ignore outliers, right? So again, here we seem to do well in terms of comparative with other methods which are existing in literature, and we were able to achieve what we wanted to, that is do co-segmentation across multiple images and not just image pairs, and also handle outliers. We try to use a graph and then segment and then co-segment. So now we switch to a slightly different approach, which essentially relies on the fact that any given image, if you think of it as a foreground and a background, most likely the object which we want to co-segment is going to be the foreground in these images. So then if we can find this common foreground, so that's the difference. So now if we can find a common foreground across all the images at the top, then that will also give us a co-segmented object. So when we take this as a foreground, everything else is together and the foreground together. And again, the way we do this is we start with something what is called as a seed extraction. That is, we have some heuristics. By heuristics, I mean, so typically you can assume that the object which is very of interest if certain size and it's not on the border of the image or the edge of the image. So use such heuristics and also kind of use the color and other features to say what a foreground object should look like, that it should occupy a certain percentage of the image and some such heuristic. Using that, we extract for every image something we call as a foreground seed. So this is not just a pixel, it's like a distribution and a collection of pixels. So we do this across all the images to get the common foreground seed by looking at all the images together. Similarly, we look at all the images together and also get what could potentially be a background. Again, here again, we have a representation based on superpixel, so that way we don't have to do computations, too many computations. Once we have this background, as I said, background can be quite different. So which means we may have many such background regions, and that's what is shown here. But now what we want to do is we want to kind of start with each of the seed and see if this seed belongs to the foreground or the background, and keep doing this in a kind of iterative way, right? And we associate it to a foreground or background based on some distance measure with between the features. Like feature, by that I mean, if you take any pixel, you can think of that pixel to have, let's say, some r value, g value, b value, and maybe like hue, or let's say the slope of the pixel, or is it a edge or some, not an edge. So such things will form what is called as a feature corresponding to each superpixel, right? So we do this in a kind of iterative way, that is to either label it as a foreground superpixel or a background superpixel, and we keep doing this and keep updating the seed. So some pixels or superpixels will move to the foreground, some will move to the background. So you can see that these things getting updated as we propagate further. Once there is no more propagation, we stop, because that's the point where we have the common object. And how do we say that something is common is by looking at kind of a, if you think of distribution, you can think of having a distribution and mode of that distribution. So here you can see, let's say in this case, a two-dimensional feature vector is considered. And if you look at the distribution, you can see there are many points here which are not very close. And there is one region which is very close or compact, right? So these regions, or the superpixels corresponding to this compact region, represent the common object, because we are assuming that the common object forms tight clusters, and so that's why this region is what we are interested in. So we proposed a way to extract this mode from a multi-dimensional distribution, and once we find that mode, we can associate points to that mode and keep growing this number of points which form this common object, right? So one thing we do when we form this common object also is to look at to discriminate from the neighboring points. So some of you may be aware of this discriminative features, or how to discriminate one point from another point. So there is a standard approach in machine learning called as linear discriminant analysis. Essentially what it does is, if you give a set of points, let's say a star and dot here, at some points are quite separated. If I just measure the distance between points, I could see that this set of points can be easily separated from these stars. But if you look at the region in between, it's not very clear, is this star belonging to the star cluster or the dot cluster. So what we want to do is, we want to make sure that the star lies far away from the dot. So this is given in our training set. So we do some kind of manipulation or some transformations so that we can clearly distinguish the star from the dot. And if that, once we do that transformation, this is how it will be. You take all the red points, you transform, it will be well separated from the dots here, right? So we need to do something similar, but now transform or use this in our pixel or superpixel representation. And when we do that, we bring different classes far away and same classes together. That is what this between class variance or across class variance and within class variance means. We minimize this within class variance and maximize this between class variance. Again, I'm not going details into this, but there are efficient algorithms to do this. And using this is kind of the final block diagram view of how we could do our co-segmentation. We are given these input images. We obtain the superpixels, which is shown in A here. We do the mode detection to find the common object. The remaining pixels, some of them will be background. Some of them we may not be very sure if it is foreground or background, because they are just little far away. But with this starting point, we start our clustering algorithm and we do our discriminative analysis clustering algorithm, so that as we iterate in the clustering process, we see you can see the image G or the left corner. You can see that clusters getting formed like green, blue, red, yellow, sorry, not yellow, black, and so on. The key thing here is there are still some points which are outside these colored clusters. So that clusters get tighter as we do this label propagation. At the end, almost all the points become blue, either green, red, or black and magenta. Now we again do some kind of, as I showed before, similar points in a cluster or in one cluster come closer, and points across clusters get far away. So that will lead us to such a representation. And we may be interested only in this green cluster because that is the main object. So we map back this green cluster into the original image, and we can get back the segmented object. So this is the approach which we use. So this is a kind of simple idea which says you find the foreground, you find the background, separate them, and you can co-segment. When you do this across all the images which you are interested in. So the idea is simple, but making this algorithm was quite challenging because finding mode in a multi-dimensional distribution is not easy. Okay, but any of this worked, and this is just as a representative example where you have this panda bear and a pyramid-like thing, and you can see that that is identified as an outlier, and the panda bears are kind of segmented out as a common object across these images. So this is again kind of an unsupervised approach, which means there was no data used for training any of this thing. So that kind of are the two approaches where we had for this unsupervised approach. So why did they do well? They did reasonably okay, but were they perfect? So we tried these images here. That is, in the left side you have a pair of aeroplane images, and you can see that these aeroplanes are looking on the side, and you see the co-segmented output images. They have co-segmented the airplane, but then there are several background regions which have also come into the output image. This was not too bad, but if you now go to the right side image pairs, the input images here, if you recall, this is what I showed in the beginning, that one is a front-looking airplane, other is a side-looking airplane. And if we use this unsupervised approach, it just based on the image features, let's say for example color and something else, it co-segmented, but you can see it's not very good. It's actually poor. Like there are many background regions which are coming into this output image in both the top and the bottom image. So this could indicate many things. One, the way we look at it is probably there is no notion of objectness in the way we did the unsupervised approach. We didn't put any measure to say where an object should end or start. Right? We did put some measure, but that is not very good enough for such challenging images. And another way to look at it is maybe this needs something more. Like maybe if I say that there is an airplane, will this do any better? Right? So those are the kind of questions which we want to address. And also we wanted to look at how do machine learning algorithms do this co-segmentation, and can we do better than this unsupervised approach if we use machine learning or deep learning. So that's kind of the rest of the talk. So we'll talk about two methods. In general, when we are talking about, so maybe most of you would know about machine learning, but for those of you who may not be that familiar, I'll just briefly say what we want to do. So this approach we are going to look at is a supervised approach. So in a supervised approach, what we have an image data set. In that image data set, we take certain images. So for example, that is the training phase. We take several image pairs. In this problem, we need a pair as an input. So if we have the image pair as the input, we will also have the object output. That is, we will have a mask which shows this is the output which is having common segment. Right? So you have a pair of image and you have a pair of mask. So this mask is like, just think of it as a black and white kind of image. You put this on the original image, you'll get the object. The white regions will extract out the object, black regions will make it black, right? So that is this pair. So for every image pair in the training set, we have a mask pair. And you have many such image pairs and you have many such mask pairs in the training. You have something called, let's say for now, just think of it as a black box, which takes this image pair input and gives us the mask. So we kind of find what this black box is from our input training pair. By doing this, what we say is this network learns a mapping. The mapping T essentially takes this input image pair, let's say Ij and II. There are some parameters which control the mapping. What the output will be a pair of masks. The mask again will be Mi and Mj with a hat at the top to indicate that's just an estimate. This is not exact, this is just an estimate. you will have mi and mj estimates. Now, if I take these mi and mj estimates, apply the mi estimate on the original I will get the object of interest. Similarly, if I take the mj and apply it on the original ij, I will get the original object, right? So in training, we have mi without the hat. So that way we can know what the object is. But what this thing tries to do is, it tries to learn a function, learn mapping function. So this is what that black box or the machine learning algorithm does. Essentially, it is trying to learn this mapping function T. Since it's learning this mapping function, you don't get exact mass. You only get an estimate of the mass, right? So once that is known, because we have trained this network using input pairs and mask, we have a transformation which will take input image. So in the testing scenario, we will take this pair of images, again indicated as ij, but more importantly te to indicate testing. We take these two images as input pairs, and what will the output be? The output will be the estimate of the corresponding masks for each of the image. So this mask, if it is correct, if I apply that on the image, test image I and test image j for the corresponding mask, we will get the object which is of interest. Right? So this is what the supervised co-segmentation approach is. Many times supervised approaches need two images, but this specific problem requires two image inputs, right? And then the output also two images which are just masks, right? So of course, again, we try different approaches. The approach which I'm going to talk about today, I'll refer this as CoSegNet, which got published in a conference, and I'll say a little more about it. But again, what is to be noted is this is not some magic. It is going to exploit this thing which we already know, that it is going to classify a given image as foreground and background, and then get this common foreground to get the object. Right? This is exactly what we did in the unsupervised approach previously. So this is really, I mean, you would see the power of this when we show the result. But let's go ahead and see what it is going to do. Since I'm not sure how much background each of you would have in any of these networks, I'm not going to go into all the details. I'll give you some idea about how this works, and if there are questions, we can revisit this later at the end of the talk. Right? Since we are using two input images, we will use what is called as a Siamese network. Of course, many of you would know about Siamese twins. Essentially, these are twins who look very similar to each other. Similarly, you're going to have a network which is a Siamese network, which means two sections of the network are going to look very similar. And then we do something slightly somewhat related to what we did before, but in a slightly network-like or a neural network-like approach. One thing which will be useful here is when we train, we have a mix of training pairs. One pair we say, or set of pairs we say as a positive samples. These positive samples mean there is something common in this image pair, and so we can use it to actually get the mask correctly. But if there is nothing common, right, then what the network should give is it should not give anything that there is common, right? So then we call them as negative samples. This will be clear when I show the next kind of testing output. Momentarily assume that we already have this network, and if this network is given this input pair, in this case a positive sample which has cars, a red car, and one of course is a front looking car, another is a side looking car. If we take these two cars as input and give that input to this network which we have designed, what we will get is we'll get a output pair which is this mask here. So you can see the predicted mask just as white and black, and again here again white and black. Now we apply this predicted mask on the input image and we'll get the object extracted, right? So this you can see is actually an output of our algorithm, and I just wanted to show that this is a positive sample output, and then instead if I have a negative input or a negative sample, which means a pair which doesn't have anything common, a squirrel here and a car here, this should not be co-segmented. And if you see the output of the network, you can see that it is just black, indicating that there is nothing common in these images, which is what we wanted, right? Again, as is noted down here, This is what I'm showing here is a testing stage. That is, this is the output of the network. So now we will just try to understand a little bit about this network. As I said before, this has a Siamese network. That is, input 1 goes here, input 2 goes here. The different layers of the network are kind of common across both these layers. They're not the same, but they are common. So the weights may be common here, but they may not be common at all points here. So we start with this. For a moment, just forget about the blocks in between these two up and down blocks, right? So, and then just think of as positive samples, right? So these both are positive sample. You can think of as co-segmenting one image, getting one mask, co-segmenting other image, getting the other mask M1 and M2. If this M1 and M2 belong to a common object, then you can see that they should be very close, right? If I just compare them, they should be very close. So we ensure that we want to be close if there is a common object. So we make a decision, is there a common object? During training, we know that there is a common object. So we'll make this one and compare this. So when we want to minimize this difference, the network will train accordingly to get the weights. Once we have that, that is kind of to say, this is like trying to measure the similarity between the mass. That is one kind of error or measure. The other thing we want to do is, we want to kind of not necessarily just what I would say find the similarity between mass, but recall that in we were looking at the unsupervised approach, we wanted to bring similar objects close and dissimilar objects far away. So here we do something similar, that we bring this metric learning means it's trying to learn based on some error, bring some feature points closer and some feature points far away. So that is this metric learning network. So that's done in this second kind of block. And the third block, as I said, is the decision block, which is, it says, is there something common or is there nothing common? So during training, we use this. During testing, it just has to be estimated, right? So sorry, this means that our training strategy also will be slightly different. And we combine all these three losses when we do kind of our training. So that is this W1, L1, W2, L2, and WL3. So L1 is similarity measure. That's what is shown as encoder decoder loss. The Siamese metric ensures that the common objects clumps together. This decision network is mainly during the testing phase to say, is there a common object or not, right? Given this kind of what I would say setup of the network, we looked at this for different kinds of data sets. Because if you're not working in this domain, you may not be aware of all the data sets, but you can assume that there are many such data sets. But the problem is they are all single image data sets. So we need to make a pair input as data set, and we had to construct some, but then we use some of the existing ones. We train using about 5,000 image pairs and test using about 1,000 image pairs. Okay? So in that, one thing is, recall that when we have positive samples, we need to make sure that similarity is there. When we have negative samples, we don't have any similarity. So that this first part will not be used in our training. Right? So given this training setup, we can test the network. Here is an output for our trained network. So this is again the image which I showed in the beginning. So you can see that the airplanes quite not what I would say not very well co-segmented. This was from our unsupervised approach. Now you can see, compare it with our supervised approach or the network which is shown. These are of course this side-looking airplanes. You can see there is no kind of background extracted here. You have almost the complete airplane extracted in this supervised approach. Of course, this does say the supervised approach does perform well, but I am not just saying only machine learning should be used. Many of our learnings which we had during an unsupervised approach helped us do this better. We ensure that this is done well. So our supervised approach also led to good results. So now we can also look at that side-looking and front-looking airplane. So here this is shown as the bottom row. So one airplane is in looking front, the other airplane is looking on the side. So if I use our network fully optimized, the output is shown at the right extreme, you can see that the aeroplanes are extracted out very well, right? Just the aeroplanes, which shows that this supervision helped us extract the common objects despite the aeroplanes being side looking and front looking. Whereas if you look at the top row, there is a horse and a house. If you just look at color wise, they seem to be similar. So some other existing approach seems to have giving this output, which is not very good. But if you look at the output of our approach, you can see that it's like a blank image, which means there is nothing common across these images. So this is again one of our recent works and which got accepted in a conference and published. So what this says is it seems that the networks have captured this notion of objectness and it has tried to learn from the input pair. Recall that in the training phase, these images would not have been there, but some similar looking things might have been there in the image pair. I mean, not exactly plain, but maybe one is they're looking at the side and so on, right? So that way, the supervised approaches do have an advantage over unsupervised approach. So we move on to the kind of last method, which I will just say. So this is motivated from the previous approach, saying that yes, supervised approach does reasonably well. Now we wanted to scale up to do the same thing for multiple images, and also at the same time reduce the number of image pairs we need for training. We may not always have a very large number of image pairs for training. So what we do is we come up with a slightly, this is again a more recent kind of approach in machine learning, which is saying few shot. The few shot here refers to looking at just few images, right? So to do this, what we do is we kind of have what is called as a guide set. So this guide set implicitly says the object to be co-segmented. So in this case, say for example, there may be 3-4 cars with images with car and one image with this snow mobile kind of thing, which is a kind of outlier. And our algorithm knows that these are common objects and they have to, we are saying, because we are saying guide set, it is going to say that these are common objects and tries to find the common object. Once it learns this common object from these few images, what it will do is you can, the way it know that these are common objects is you give a co-seg set with that. So for example, if you kind of give a co-seg set, then it can identify what is the common foreground which matches with the guide set, and then what is not common with the guide set, right? So this is something which was something recent. We're still trying to, this is work in progress. We're still trying to publish this, but you can see how it does well. So for example, here you are given 6 images because it was the guide set which had cars predominantly. You can see the bullet and this other engine like thing did not get co-segmented, but the cars in all these images was co-segmented, right? So guide set as, is it like a guide? It says, okay, implicitly says that these are my common foreground and these are my outlier. So do what you can to do the same thing on this bigger set, right? Of course, this doesn't happen kind of in a very easy way. We need to do quite some things which are much different from the way we did in the previous set. I don't, it may be difficult to get across all the points here, except saying that what we did in training in the previous phase, here we do it with a fewer images. Since we are doing this with a fewer images in a slightly different way, the network gets quite complicated and it has to become more intelligent, right? So that is why all these things are there. One thing you can see is like attention. So what this attention tries to do is it tries to say if a given image and if I mask, my mask says horse, it will try to find what in the image created this mask. So it's like how we humans do, we try to pay attention. Similarly, the network tries to pay attention to this region. And similarly, it will also try to pay attention to the dog, but it will say, I'm not going to use it, right? Something similar is happening in the network. And we can do this with a fewer set of images than compared to the previous image. So again, this is just to illustrate that the number of images which you have in the guide set, let's say for example, it could have been 2 images or 4 images or 6 images or 8 images. If these images are more, the better you have the co-segmentation output. So, for example, in the case of 4 images with common object, we seem to do well. Of course, what we wanted to show here was we introduced a modification which led to better co-segmentation performance compared to what is done usually in the literature. So here you can see the guide set, and the guide set had more of this pyramid images like this one and this one, and it said that this horse is an outlier. So now if this, with this input as guide set, if we have this as a co-segment set, you can see that in the output from our network, we only have the pyramids extracted. If we don't do everything we did, we may end up with extracting the horse. So this is why I'm saying our learning from the unsupervised approaches helps us further refine the supervised approaches and make it a more powerful network, as you could show here, and we get better results. So here is another example. Again, you can see that the first 2 rows are the 2 different co-seg sets, which means we want to co-segment them. That this has like horses predominantly, and the second row has aeroplanes predominantly. When we tried on this, we used the guide set which is shown on the left, which predominantly has horses. So when we use this as the guide set, the output, as you can expect, extracted out the horses. And when we use the guide set as the aeroplane for the second row, it extracted out the aeroplanes, but did not extract out these other outlier objects, right? Of course, this is just an illustration. We showed that objectively, like performance measures also improved using our approach. And this seemed like a promising approach when we have only few images to guide our co-segmentation problem. So that kind of brings me to the end of this talk. So I started off with defining the co-segmentation problem, showed you some illustration, and I showed you that unsupervised methods did reasonably well, but we realized that the features which we use are very important, and the results may not be perfect. So then we moved on to look at supervised methods. There we looked at 2 different approaches. One approach which uses large number of training images, which did reasonably well. And then we moved on to another method which we call as few shot segmentation, where we have a smaller training set or a guide set. A smaller by that means fewer images in the guide set. So we are continuing to do some of this work. One of the work is whatever I've shown so far is one object in across multiple images. Of course, you can extend this and see how if you have multiple images and multiple common objects, how do we extract it? This is going to be quite challenging if you look at it as an unsupervised approach. But even a supervised approach is going to be challenging. The other kind of extension which we want to do is, if you're given videos and we want to co-segment, can we do this effectively? So that's again much more challenging than the image-based co-segmentation, because there, in addition to space, you have time as well. Whether or not to consider time is one important thing you need to make a decision on. So that's there's some publications out of this work, and I would like to thank you for listening patiently. And at this point, I'd like to take any questions you might have.
Yes, sir. Thank you for information. Hope all participants have got something new today. Dear participants, kindly share your questions, please. If you need to talk with us, there are 2 persons given request. One is N. Archana, then Havala. Both of them are enabled. You can join now. Others can send message, text a question through the chat box. I have enabled Archana and Havala. Can you share your questions, please?
Okay, I'm looking at the chat. I don't see any questions. So.
Yes, that's waiting. Any questions, please? Okay, sir. I will consolidate questions and send
Sure,
to you,
yeah.
sir, when I receive the questions.
Okay.
Now, as of now, no questions from participants. Okay. Thank you very much
Yeah,
for
okay.
accepting our
Yeah, thank
invitation,
you.
sir. Thank
Yeah,
Yeah.
bye.
Thank you, sir. Thank you, sir.